Hi everyone, welcome to the video. For those of you who don't know me, my name is Arda Kurtoğlu and I am a first year physics student at the University of Oxford. This video is the second video on a new series on this channel where I share stuff that I learned during my physics degree. In this video we will go over Maxwell's equations in vacuum and see how that leads to a wave equation, so how that leads to electromagnetic waves. Without further ado, let's get into the video. Alright, to start off, I will first write Maxwell's equations in general and then we will consider what happens for a vacuum. The first one is known as the Gauss's law, and I write it in the differential form. So we have that the divergence of the electric field is equal to the charge density over epsilon naught. Then we have the Gauss's law for magnetism, that the divergence of the B field equals 0, which physically means that there are no magnetic monopoles as far as we know today. And then the second one, so the third one, so the curl of the electric field is equal to the minus time derivative of the magnetic field, which is known as Faraday's law. And then we will have the Maxwell Ampere law, so the curl of the B field this time is equal to mu times the current density, mu naught times the current density. This is Ampere's law, and then Maxwell added the displacement current term, which says that if you have a changing magnetic field, you get a changing electric field. And this is incredibly important for us to get magnetic waves, and you will see that hopefully during the derivation. Cool. So now, these are the general formulas, and I want to consider them in vacuum. So in vacuum, I think that's how you write vacuum. I hope so, at least. And so in vacuum, there is no, so rho is 0, there is no charge density, and J is 0, there is no current. So that's 0 and that's 0, okay? And this is quite important for our derivation, as you will soon realize. I want to consider the curl of the electric field, let's say. I mean the curl of the electric field. So the curl of this equation. And that leads to, well, we have a double curl. And in the last video, I derived a vector identity for this. I strongly suggest that you check that video out from the descriptions part or from the cards. And so that's going to be equal to, I'm just copying the result that we proved in the last video. It's equal to this, right? And the neat thing about this is that since we are in vacuum, this part is 0. So we have minus the Laplacian of the electric field on the right. That's the right side. And on the left, this is equal to, using Maxwell's third equation, this is actually equal to the minus time derivative of the magnetic field. And that's equal to the minus Laplacian of the electric field, as we just showed. Here, the nice thing is you can switch the order of differentiation. Meaning you can take the d by dt out, and then you will write this. And I put the minus sign there. Right? And you might be concerned about this, but the thing is, this will give 3 components. We are working the Cartesian, right? This will have 3 components. All will have like derivatives with respect to x, y, and z, and then with respect to time, a different combination of these. And it's a well-known property of partial differentials that the order of differentiation doesn't matter for well-behaved functions, let's say. I'm not really that familiar with the mathematical rigor of it, but for well-behaved continuous functions, it's the case that the order of partial differentiation doesn't matter, and there is a very short proof of it which I can share in a future video. So if you would like to see that, please let me know. But anyways, so that's that. If you weren't confused, don't let yourself confused. If you were confused, I strongly suggest that you write out the components and see that it's just a matter of the differentiation order, and it doesn't matter for partial differentiation. Okay, so this minus sign becomes a positive. Then we have d by dt of Well, the curl of B, we know what that is. It would have been that, but since we're in vacuum, the first term is 0. So we just have epsilon naught, mu naught, and then that. And well, the nice thing is, mu naught and epsilon naught are obviously constant, so you get this equation, which is a wave equation. Now, I would write this this is a wave equation, literally. So we've shown that the Maxwell's equations in a vacuum leads to electromagnetic, to electric wave, to a wave equation for the electric field. And you could do the same thing for the magnetic field. And I'm not going to do it. That's like an exercise left for the viewer, let's say. And it's the same process. You will just take the curl of this equation. And I really suggest that you do that. And when you do that, you will literally get the same thing with the E's replaced with B's. And I want to highlight one thing as well. I'm not really going to discuss about the solutions of this. There are multiple ways about how you could go about solving it. Like you could consider it for a linearly polarized plane wave, let's say. And it's the simplest one, I guess. And it's quite informative to do so. I can do that in a future video. But I just want to highlight one thing. It's a property. Well, as I said, if you've seen wave equations, you will know what I'm talking about. And if you haven't seen them, this might be confusing to you. But in this general form, this part is the speed of propagation, speed of the waves squared, which we denote with c squared. And which means that c is equal to 1 over epsilon naught mu naught under the square root. And if you were to plug in the values for epsilon naught and mu naught, you would see that you get the familiar value for c, which is 3 times 10 to the power of 8 meters per second, approximately. And so this is the well-known speed of light, which is great because we know that light travels at the speed of light, and we've shown that these electromagnetic waves also travel at the speed of light, which kind of, you can see that implies that light is an electromagnetic wave. So this is pretty cool. So anyways, this is it for this video. What you should do now is hopefully derive the same equation for the magnetic field. And also if you want to see how this can be solved by a linearly polarized plane wave, then let me know in the comment section, and I hopefully will do that in a future video. But anyways, thank you for watching the video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.